What's up, guys? Welcome back to another Algebra 2 instruction lesson here with Mr. Gaines as we continue to look at exponential and logarithmic applications. Today's video is going to focus on the manipulation of percentages. In some instances, percentages are given to us in a certain format, and we may want them in a different format. And in such cases, we need to be able to manipulate those percentages. So let's take a look at problem number 4. Problem number 4 says a population of wombats is growing at a constant % rate. The population on January 1st of a given year is 1,027, and a year later is 1,079. What is the yearly % growth rate to the nearest tenth? Well, in this case, we can go back to a formula that we discussed in the first video dealing with a constant growth, and that is Q of t, the quantity over time, is equal to Q sub 0, the initial quantity, times 1 plus or minus the rate, the percentage rate, to the t power, where t represents time. So for problem number 1, it wants to know what the growth rate, the % growth rate to the nearest tenth of a percent is. Well, what we can do here in 1a is we can substitute in the values. We know that the quantity over time, the resulting quantity after a year, is 1,079. And we know the initial quantity is 1,027. What we want to solve for is the rate here. So we know it's a growth rate, so 1 plus r, to the t power. In this case, t is 1. It's to the first power. So what we can do is we can go to the calculator here. And if we want to get r by itself, we would first divide both sides by 1027. So 1079 divided by 1027. And I'm going to leave this decimal in my calculator for right now. I'm going to write down the rounded answer. It's approximately 1.05. And then I would subtract 1. So the rate, r here, is approximately 0.0506. It says round to the nearest tenth of a percent. So if we wanted the percentage of this, we would move that decimal place over 2 spots. And so this would be 5.06, which is 5.1%, approximately 5.1%. So we can find here that the population of the wombats grows 5.1% per year. Now in B it says use the yearly % growth rate found in part A to determine the population after a decade. So a decade, remember, a decade is 10 years. So we want to know the quantity after 10 years. So this would be the initial quantity, 1027, times, and we'll use our percentage rate, our approximate rate here, 5.1%. So times 1 plus 0.051 would be 1.051 to the 10th power. And so we can evaluate this using the calculator. Now again, this is going to be a rounded answer because we did round our percentage. And we get that this is going to be approximately, let's go ahead and just round to the nearest whole number. Let's approximate the population at 1,689 wombats. And this is after 10 years. So we can jot that down. In part C, it says, using your answer from part B, what is the decade % growth rate? So we know that we had a growth or a population of 1,689, and we started with 1,027. So if we want to find the decade growth rate, so this would be for 10 years, we're going to take the population that we ended with, 1,689, and substitute in the formula for Q of t. And this time, instead of taking t as 10, we're going to take t as 1. We're going to use t as 1 because that would give us the rate here for a decade or 10 years. So I can divide both sides of this equation by 1027 to get, we're going to approximate again here. Let's say 1.64. I'm going to leave that number in my calculator again. It's approximately 1 plus r, and then subtract 1 to get r is approximately 0.6445. So if we rounded this above, sorry, let me do a little bit better labeling. Let's say this is a 5.1% yearly growth. So in A, we found the yearly growth. Now in B, we are finding the decade growth. So 64.45, or let's make this 64.5, approximately 64.5% decade growth. And so what we're able to do here is we're able to manipulate these percentages to show how the population is increasing first over a year and how the population is increasing over a decade. Now, there is a shortcut to doing this. The shortcut would allow us or keep us from having to find Q of T first, then substituting into the formula and then changing the decade growth. What we can do in this instance is if we want to find a growth rate, and we already know a previous one, we can focus on just the 1 plus R portion of the equation. So an alternate method is to just focus again on just this portion of the equation. So if I know the yearly growth rate, so let me show you again a second way to do this. Let's say the yearly growth rate, I'll let it be Y. Y represents the yearly growth rate, and this would be 1.051. That's what we found. Well, if I want the decade growth rate, that would be Y applied in the formula 10 times. And so if I want Y to the 10th, or the decade growth rate, I can take my yearly growth rate to the 10th power. So let's take a look at what happens here in the calculator. So if I have the growth rate for 1 year and I take it for 10 years, this was the yearly growth rate, and Y to the 10th gives me, let's just call it D for the decade growth rate, which is 1.644. And now again, we did round some numbers, but we can see that if we did not round, this is actually going to give us the decade growth rate percentage here that we found in C. It's a shortcut. So in C, we first found the population after 10 years, and then put that back into the formula and solve for R. And it's rounded a little bit because we rounded some of our work there. In this method, we just go straight from finding the yearly growth rate into converting it into a decade growth rate. So in part D, it says, assuming the growth rate is constant over time, what is their monthly growth rate to the nearest 10th of a percent? So let's use the shortcut method here. So what I would want to do here is take a look at the yearly growth rate. And again, the yearly growth rate is 1.051. Well, the monthly growth rate is going to be less than a year. The monthly growth rate would be 1/12 of a year. So what I want to find here, if I want the monthly growth rate, this would be the yearly growth rate to the 1/12 power, as there are 12 months in every year. And so what I would do is I would take my yearly growth rate to the 1/12 power, and this would give me my approximate monthly growth rate. So 1.0042 if we approximate things. So the monthly growth rate would be approximately 0. If we round to the the tenths of the percentage. Remember, this is the representation of 1 plus R. So we would subtract 1, we'd be focused on just the decimal point of this. The yearly or the monthly growth rate would be approximately 0.4%. And we can test this. So let's test this by substituting in my initial quantity, using my monthly growth rate, and seeing what the population would be after a year. And again, we did round a little bit. So if I take Q of T, and I substitute in 1027, and then I use 1 plus 0.004, which is 0.4%, to the 12th power, to represent 12 months that this would occur at, you can see that this number is very near the same number that we had for the 1 year population. Again, the numbers are slightly off because we did some rounding. If I went a little bit further on this, if I went and put the 2 in here that we had, it's going to be even a little closer to that population. So we can see that this method gives us a monthly growth rate that does check out to match our yearly growth rate if we're trying to find population. So this is how we can go about manipulating percentages, by taking a growth rate that we know and manipulating the exponents to represent a different time period. So in problem number 5, it says a given population has been growing at a constant rate of 22% every 5 years. Determine the percentage growth rate over a 2-year time span. So what we know, let's let 5 years, the 5-year growth rate, again in that equation, let me jot this equation down here. Q of t is equal to Q sub 0 of 1 plus R to the t power. If we're focused on growth rate, it's just this portion. So the growth rate, let's let f, actually let's let y equal years. Let's let y equals years. So then this would be 5 years, so y to the 5th power would equal 1 plus 22%, or 1.22. So this is the growth rate for 5 years. So I let y equal 1 year. And so the y to the 5th would be 1.22. So if I want the yearly growth rate, what I would need to do is I would need to essentially get y by itself, or take the 5th root of both sides. And so the yearly growth rate would be the 5th root of 1.22, which we know is 1.22 to the 1/5 power. Now, if I want to find this is the yearly growth rate. Now, if I want to find the growth rate over a 2-year time span, 2-year time span would be 2 of these applications, so y squared. So y squared would be 1.22 to the 1/5 squared, which we know with our properties of exponents would be 1.22 to the 2/5 power. And you can get here in less steps. If you realize that 2/5, a 2-year time span is 2/5 of 5 years, then you could take that 1.22 and go right to the 2/5 power. Either way, we're going to get to 1.22 to the 2/5 power, and this is going to represent the growth rate over a 2-year time span. And so if we calculate this, this is approximately, again, y was a 1 year, so y squared over 2 years would be approximately 1.0828. Usually we round to 2 decimal places. So the percentage growth, if we move this into a percentage, remember again, this is 1 plus r, so we would essentially subtract 1 here to see just the growth. The percentage growth would be approximately 8.28% growth every 2 years. Sorry, I wrote that a little bit on a slant there, but we see this process here, focusing on just the rate portion of the equation for exponential growth or decay, and starting to manipulate exponents to change our time domain. Let's take a look at another example. In problem number 6, it says, because fruit flies multiply very quickly, they are often used in a study of genetics. Given the necessary space and food supply, a certain population of fruit flies is known to double every 12 days. If there are 100 flies to begin, find the growth rate and the number of days until the population reaches 2,000 flies. So what we know here, let's let D equal day. What we know is that the population doubles every 2 days. A double tells us that it's going to have a 200% growth. It's going to multiply the population by 2. So this is every 12 days. So day, D is 1. D to the 12th, again, we're manipulating the exponent here to represent the time domain. D to the 12th is going to equal 200%. or d to the 12th is equal to 2. It's going to double. So what we want to find is the growth rate, and we can go ahead and put this in the number of days because eventually we have to find the number of days. So let's find the growth rate per day. So if I wanted to find the growth rate per day here, I would have to get d into a single power variable. So I would take the 12th root of 2, which we know is 2 to the 1/12th power. So 2 to the 1/12th we can evaluate in the calculator. This is approximately 1.0595. So the growth rate is approximately 5.95%. Again, this represents 1 plus r. So we would subtract the 1 and focus on the percentage, 5.95% per, or let's say growth per day. And now I'm going to leave that unit in my calculator because eventually I'm going to come back to that. But this is part of the question. The other part of the question is to find the number of days until the population reaches 2,000 flies. So again, we're using that, we want to find that quantity over time, which is q sub 0 times 1 plus r in this case, because we are increasing the population to the t power. And so in this case, we have the quantity over time is 2,000. We know that we have 2,000 flies. We know that the initial population was 100 flies. And we want to solve for the time. So we can use our growth rate that we found here. 1 plus r is 1.0595 to the t power. Now, a couple of ways that we could do this. We could go ahead and solve this algebraically, or we could solve it graphically. I'm going to go ahead and solve it algebraically in this case. So what we would do is we would divide both sides by 100. So if I divide 2,000 by 100, we get 20, equal to 1.0595 to the t power. I need to get t out of the exponent, so I would use a logarithm, a log with the base that we have of our exponent, 1.0595. And I would take that logarithm of both sides. On the right side, that would give me t out of the exponent. So now I can evaluate this expression to find the answer for time. So what I'm going to do here is, notice that we're going to need the change of base formula. So I'm going to use the change of base formula to evaluate. This would be log of 20 divided by log of 1.0595. I'm going to try to be a little bit more accurate here. I'm going to go up and select that value in my calculator. If you select the value there, or you can use the second answer key, it's just going to take that rounding out a little bit further than what we wrote down. Now, if you were to type in 1.0595 on a quiz or a test, I would have that answer as part of the acceptable answers, but we want to be as accurate as we possibly can here. And if we use that number in the calculator, we get a better representation. So let's go ahead and round this to 2 decimals. T is approximately 51.86, and our units is days. So it takes approximately 51.86 days to reach 2,000 flies. So there we have a use of the manipulation of percentages. We know how long it takes for the fruit flies to double. And instead of just finding the time that it takes to double over and over and over again, that would not get us to the 2,000 flies that we want. So we manipulated the percentage down to the nearest day, found the percentage growth per day, put that back into our equation for exponential growth with a constant percent, and then solved for time. Let's take a look at one more example here. So example problem number 7, it says the radioactive element potassium-42 is often used in biological experiments since it has a half-life of only about 12.4 hours. How much of a 2-gram sample will remain after 18 hours and 45 minutes? Well, if we want to, we're talking about the half-life in hours, so I'm going to go ahead and convert this last unit of time into just hours. 45 minutes is actually 3/4 of an hour, so 18.75 hours. I'm going to come back to that number. If I want to find out how much will remain after the 18 hours and 45 minutes, I can use my exponential equation for the quantity with respect to time, which is q sub 0 times 1. In this case, it's decaying. The half-life means it's reducing, so this would be 1 minus r to the t power. Now what I know is the initial quantity. The initial quantity is 2 grams. I also know that my time would be 18.75. What I don't know is my rate. So in order to find my rate, now I'm going to use some manipulation of percentages. So let's let h equal hours. And what we know is that it has a half-life of 12.4 hours. So every 12.4 hours, or h to the 12.4 power, the amount is cut in half. It's 50%, so 1/2 or 0.5. Let's go ahead and just do it as a decimal. That's 0.5. Now, if I want to find the hourly growth rate, the hourly growth rate is going to be useful because in my problem, I have my time domain in hours. So to find that hourly growth rate, I'm going to take each side, the 12 or 12.4 root of each side, or if we remember, that's going to be the same as a rational function 1 over 12.4. And I know sometimes we don't like it decimals in fractions. I believe our calculator will do that for us, but that would be the same as 10 over 124 or 5 over 62. But this can find the hourly growth rate. So this is 0.5 to the 1 divided by 12.4 power. And this would be an approximate hourly growth rate of 0.945 63, etc. Let's just list this as 0.9456. So this is the growth rate. Again, in this case, it represents 1 minus r. So this is not actually the percentage growth decrease. It's just a change that's going to happen on an hourly basis. So we can go ahead and put this in for 1 minus r. We know this is 1 minus r because it is a decrease. So if I want to evaluate this expression, now I can figure out the amount that's going to remain. So I can take 2 times the 0.9456. To be a little more accurate, I'm going to use that decimal that's left in my calculator. I'm going to take this to the 18.75 power. And we would find that approximately 0.70 grams of potassium 42 will remain. So what we did here was we converted the growth rate, the decay rate that we knew into an hourly rate, used that hourly rate in our exponential growth or decay equation, and then found out how many grams would be left. So there are some examples of how we can use percent manipulation to rework problems into a manner that we can solve a variety of different perceptions or a variety of different example problems. Okay, so if the time domain is given or your growth rate is given with a different time domain than you need to solve, we now know how to manipulate exponents to be able to solve those equations. As always, thank you guys for tuning in, and I'll see you soon.